Hello and welcome, guys. So this is going to be a second video about WebSockets against service and events. And specifically in this video, I will focus on sending messages with compression. So in one of my previous videos, I got a message from Anders and he was asking if I was using broadly compression over a lifetime of the stream. And actually, I didn't use compression at all. So I thought, why not do the testing? And I was quite curious how it's going to turn out. So in this video, I will test RAM against, I will collect RAM and data out for 900 connections, 50 kilobytes and 1 message a second. I will do a compression for the entire stream of service and events. For WebSockets, I'm going to use a native library. So it uses gzip and it will be per message. So message, right? And this is for the entire stream. And then I will also use broadcasting. So imagine we are sending like a stock update data or newsfeed, and we need to send it basically for all users who are subscribed. So we have like all 900 connections subscribed to this newsfeed, and we don't need to compress for each and every single one. So I will pre-compress message and send to all of them. And then I will also discuss when to use compression or when not to use it, because at a certain point, EC2 cost becomes kind of irrelevant and data out cost becomes way higher. And this is if we are talking about hosting your servers somewhere in the cloud like AWS. All right, and you are probably wondering what is compression per stream, what is per message. I prepared a small diagram, so let's assume this is a way oversimplified explanation of compression. So we have a message AAA, BBB, CCC, right? So what we will do, we will create some kind of dictionary where we will create pointers to each letter, right? So let's assume the A will have this pointer, the X will get the B will get X pointer, and then we will say that our message compresses to 6 stars and 5 X's, right? And then we will decompress it. So when this is what happens when we're compressing per message. So each message will have its own dictionary, and we will do this for each and every single message. So when we are doing this per stream, so let's assume here we will have A, and per stream we will have one dictionary which can recognize similar patterns between the messages, and then we can basically be more efficient with compression because we have a large dictionary. We already know how to compress this certain messages, this certain text, I don't know, numbers, whatever. So if we are talking about advantages, disadvantages, there is always trade-off, right? So in terms of advantages, in theory, we should have lower CPU because we will have a compression algorithm that maintains state across many messages. It should be more efficient, once again, because we have repeated fields, similar structures, we should recognize them and use them, and we should get a better compression rates. That's in theory. And anyways, the disadvantage is that we might have a bigger RAM overhead. Well, it depends, obviously, on message frequency, message size, what kind of messages we are sending, and things like this. But in theory, right, to have a state for all these messages, we need to have a bigger dictionary, and this big dictionary can become larger than per message. It depends as well on garbage collection, once again, on message size and frequency. And for per message, right, the only problem as well with per stream that we can get a potential buffering because compressor may hold data until buffer fills, right? So it can hold some data, and then once it's filled, it will flush it out. And per message, pretty much the opposite, right? So we can get immediate transmission. We compress one message, we send it out. We should, once again, have in theory a lower RAM usage. Once again, it depends on GC, message size, frequency, etc. And in terms of disadvantages, we will probably have higher CPU because we need to compress each message, right? It's not as efficient as for the entire library, for the entire, stream. And we can, in theory, have worse compression rates. All right, so this is the intro for this video. Now let's discuss my changes in code, how I'm doing the testing, and then we'll go into results. All right, let's start with WebSocket setup. So I had created 2 services, one with compression, one without compression. The only difference is that here in Gateway, I have compression settings. So I enable compression, I enable per message deflate. I'm setting up some configurations as well on after init, right? I'm creating these ones as well because I had some issues that compression wasn't working. And until I added all of this, it began to work actually. I don't know if it's a problem with my minukube setup. I feel like it is because I had some problems with Nginx and I had to add Haproxy. Nevertheless, it's working right now. So what we are doing here, we're subscribing to message. right? And then once we receive this once, I'm getting this from the client in the beginning of the test. I'm getting some settings like messages per minute, and then we are emitting messages. So essentially every minute here, usually I pass 60 here. So we are emitting not every minute, every second, sorry, and we are creating large payload and basically sending it to the client every second. So client is not sending anything back to me. So essentially I'm using it as SSE in the same scenario. And I've added another method to subscribe to newsletter. I will show the results as well. So why this different is that we are not sending message to each client individually. Right here, we are creating new message every single time, right, for every interval. And here is a bit different. We are collecting all the connections. We are recording them into set. And then here I have broadcast to WebSocket. So we create one compressed message, and then we send it to all the connected WebSockets. Right. So here I was playing around with compression. Either I'm doing it in the Nest using Broadly, or I'm doing it using native WS compression. So as far as I know, WS compression is gzip. So they will obviously provide different compression results. So Broadly should be, well, it depends on the settings, right? But should provide better compression, but it will have higher CPU and memory usage. All right. And the second service in terms of WebSockets is pretty much the same, right? But I don't have, it's a different namespace. And as you can see, I don't have any compression settings here. And then I have the same handle message, right? I'm emitting message every second. So all the same. And once again, I have a subscribe to newsletter. And I have it in both, right? Because I was testing, once again, WebSockets with its native compression. And if I'm going to be doing compression, and then compressed message will be sent. Obviously, if I'm sending compressed message over WebSockets, then client has to uncompress it, right? So it adds additional work for a client, right? Additional usage of CPU and RAM on the client. But nevertheless, I wanted to see the results. And then we are moving to SSE. So here I didn't change. Well, okay, I could change a lot actually here. So here I have time Broadly, right? And we are doing the same. We are emitting message every second. And I created a Broadly stream in the application. I tried to, where's my main? Yeah, so there is a compression middleware. I installed it, and yeah, there are settings for gzip, Broadly, whatever, and it should compress everything. As you can see, I'm filtering by text event stream, and it should apply to all SSEs. I tried different approaches to configure it, right? But it's, I don't know, it didn't work for me. So I had to apply compression by myself. So I created Broadly stream with the following settings. This is like a medium level of compression, I would say. Right? You can apply higher, then you will have higher CPU and memory usage. But I didn't go higher because you will see why. So I'm piping it up, creating stream, flushing stream. So this is not ideal, obviously, because we are flushing, we are deleting the compression dictionary, but I have no other choice for stream. I need to signal somehow that the message ended. And yeah, then we're creating some cleanup, etc. And time no compression is pretty much the same, right? The only thing I'm not creating any stream here. And I have the same newsletter like in the WebSockets. So we are creating SSE connection. The only difference that for SSE, I need to loop through all the connections and then send response to each one of them. With WebSockets, it's much easier, right? Because my server knows about every single client and I can just emit, and WebSockets do it internally. So, well, you will see that they will perform much better in this scenario as well. All right, this is pretty much it from the setup. If you're curious about Kubernetes setup, I've created a Haproxy. So yeah, I'm not going to go through it, but it's going to be here, Haproxy config and Haproxy deployment, because Nginx wasn't working. I'm not sure why. Probably it's my skill issues. But yeah, I wanted to try Haproxy for a while, and I thought, why not? So I applied it, and it's working. The only thing for NestJS, I increased memory usage. You will see why once again, to 4 GBs. And yeah, I increased as well old space size to 4 GBs. All right, this is pretty much it from the setup. Now let's see the results. All right, so since in the previous video we established that WebSockets were performing better with small messages, here I started testing straight away large messages over 10 kilobytes. And for the small messages, obviously, not obviously, but probably you're not going to use compression, right? What's the point? It's just going to add an overhead. So I was using 10 kilobytes messages straight away. And also I have updated my dashboards. As you can see here, this is the old one. I'm using RSS heap memory. So this is a memory dashboard. Then I was using the Haproxy bandwidth out. So megabytes out. I was using specifically this metric because I wanted to see the network out, because this is what AWS charges you for, or other cloud provider. So I wanted to see essentially the trade-off as well between RAM, CPU usage, and bandwidth. So what's going to be more expensive? And here I was as well one more dashboard with just memory breakdown. I don't record all the memories, so they're not going to correspond one-to-one probably to each other, because like I have external memory and array buffers, and array buffers are part of external memory, but I wanted to see the breakdown, how they grow with one another. All right, so I have this dashboard screenshot here, so I can edit it. And as you can see, I started with 10 kilobytes. I was going from 500 to 900 connections, and I was starting like one message per minute, so 60 messages a minute or 10 messages a minute. And I would say that it didn't matter, right? In relative terms, they were performing the same. So as you can see, I hope it's visible. So we have 150 megabytes of RSS, and here maximum we have 120 megabytes out of bandwidth. And on the left, these are WebSockets, and this is SSE, right? These are two tests. So as you can see, they are growing pretty much linearly. And in relative terms, if I compare this one to this one, they were kind of the same, right? If I was comparing this to this. So in the end, I decided to test just the last one. So this is 900 connections, one message per second. And I decided, so since in relative terms they were the same, I just took 900 connections and tested all of them against each other. All right, now let's see the results. So the first one I did without compression, just to see that, yeah, everything is working. So no compression we did before. As you can see here, I am getting, where is it? 250 maximum, right? It reaches up to 250. And in terms of bandwidth out, it's 1 GB, right? So this is 1,000 megabytes. And pretty much I got the same, right? I was running this similar tests. So I reached up to 1,000 here as well, bandwidth without compression, which is kind of okay, right? And in terms of memory, it's 150, right? So 150 against 250. So WebSockets, we established this before. They were working better without compression. So then I applied compression. And here where it gets tricky, let's look at WebSockets first. So here I reached to 500, right? So straight away you can see the RAM usage is more than tripled for 900 messages, but the bandwidth obviously decreased, right? So the bandwidth went 3 times lower. So we went to 300, right? Just a little bit over 300. So bandwidth dropped 3 times and RAM CPU usage increased 3 times, 3x. So this is a trade-off. And as you can see here, now we got it. Previously, we were using only the old space used. So this is the memory our Node.js application is enabled to clean, like timers, which I had intervals and things like this. The payloads I was using. And here you see the memory breakdown is different because we are using compression. Now we have native C++ allocating buffers for dictionaries for compression. So the memory breakdown is a bit different, which is corresponding correctly. And now we go into SSE. And with SSE, I don't know if you can see, but it's 4,000. So the memory just blew up. In terms of bandwidth, actually bandwidth is way lower, 125, right? Because here I'm compressing the entire stream. So I created dictionaries for each and every stream, and compression was better. However, 4,000 GBs, well, I'm open-minded, right? Maybe I was doing something wrong. I tried to use different approaches, but as I said before, right, I tried to apply, where's my main compression like this to entire HTTP. It worked for regular HTTP, but it didn't work for event stream, for SSE essentially. Yeah, so I was forced well, maybe I don't know something. Once again, I'm open-minded, so I created stream for every single connection. And it just blew up the memory because in this case, I'm creating these dictionaries, buffers for every single one of them. And it's a few megabytes, like around 5 megabytes per connection, and then 900 times 5, and you get 4 GBs, right? Approximately. Obviously, you can decrease compression rates, but then you will have bigger bandwidths, right? So essentially, like, what's the point of compression in a sense? But well, you can play around with this, but I guess that's not the problem. The problem is that you're still creating buffers for each and every single connection. So this is quite inefficient, right? So either I'm doing something wrong, or I'm not sure if compression over the entire stream is valid, or maybe it's done in different programming language where you have more control, because I was trying different approaches. As I said, I tried to compress the entire HTTP and just didn't compress the SSE. It was compressing HTTP, the regular request, but not SSE. And I see that, I know the use case is very popular because, for example, Claude, as you can see, right? So here I was sending a message, I checked it out, and they apply compression, but I think they're applying compression per message. Or if they're using stream compression, I'm assuming they're not doing it in application, like I'm doing on application level in NestJS. They're doing it most likely on transport layers or Haproxy or Nginx. And I'm sure you have way more control there. For example, I checked that Haproxy is written in C, so you can manage buffers and everything internally way more efficiently than JavaScript. But basically in JavaScript, I don't have any control, right? Maybe once again, I don't know something, but my hands are quite tight. And I'm sure in C++ or in C, which is Haproxy, you have way like more options. And also I checked that since Claude is using Cloudflare and they have CDN all over the world, they have CDN optimizations specifically for streaming. So probably that's another reason. And I checked that these optimizations, they apply better to HTTP than to WebSockets, but it's not guaranteed. It's just, I checked with the AI and that's what it told me. Nevertheless, I can't test this all by myself. I just tested it in application level, and that's why I got results like this. I'm sure, they are not using SSE streaming like I do. Nevertheless, I wanted to test it out. And also, I think they're using SSE because from what I read as well in different articles, cost of reconnection for SSE and WebSockets is lower. So, for example, SSE should use like around 2 to 5 kilobytes of RAM, and WebSockets use about 5 times higher, 2 to 5 times higher. And maybe I will test it out in another round, but for now I didn't test it out. I just tested for now just how streaming compression works on application level. And as you can see, they are not keeping persistent SSE connection for, I don't know, extended period of time. They just gave me a response and disconnected, which makes sense. However, this forced me to think, right? I thought about what if we will use SSE with compression ahead. So that's why I created a newsletter broadcast, and to see how it's going to work if we will broadcast a pre-compressed message to all the connections. And this is the final test I wanted to show you right here. So when I was using 500 kilobytes, 900 connections, one message per second to all available connections. Actually, SSE, you can see the memory was not that high. It's 150 megabytes, and it didn't even reach it, right? And in terms of bandwidth, it was varying, right? But overall, on average, it was around 200 megabytes. So, which was pretty good, like compared to here, right? The compression rate is not that high, but we have only 100 megabytes of RAM usage. And when I was using the WebSockets, results were pretty much the same. I got, maybe if I'll run more tests, so it was around 225 in terms of megabytes, the bandwidth. And in terms of RAM usage, you can see that it's the same, which should be the same, right? Because I pre-compressed one message and then sent to all available connections. And I just tested out as well WebSockets. What if I didn't compress message ahead of time? I just sent same message and enabled compression for WebSockets. And then, it didn't work out. I thought that maybe they will recognize that it's the same message, but apparently not. They were compressing each message individually. I mean, WebSockets for native library. and bandwidth was actually quite high as well, like 330. So yeah, if you're broadcasting messages for all the connections, pre-compressing it was way better overall. Yeah, and as I see myself, like SSE performed quite good, but not if I'm compressing the entire stream. If I'm compressing message and then I'm sending compressed message. Once again, I'm open to discuss it. All right. So the final part, let's move into conclusions. And also I wanted to discuss, as you can see, that compression is not a silver bullet, right? It's a trade-off and when you should do it. All right, so here is the diagram with the results we just saw. So the first one was WebSockets, no compression, no compression. So we have RAM as red and bandwidth as green. And here we got pretty much the results for bandwidth were the same, but we got a bit of a better performance for WebSockets in terms of RAM. So about 30%, I would say, like 30% on average was better. And this is, I guess, what was in the previous time. But with compression, the results were very different, right? So here I wrote up to 1,000 because, yeah, actually here was a 4K. It just wouldn't fit in the graph. It was just way too big. We wouldn't see anything else. So here we got way better results in terms of bandwidth, but just RAM usage is, yeah, exploded. But the important part here is if we look at no compression against compressions WebSockets, right? If we will look at RAM usage, it jumped as well significantly, right? Like 3x, it went higher. The bandwidth as well decreased significantly from here to here, right? So essentially what I'm trying to say that it's a trade-off. We reduced bandwidth, but we increased RAM and CPU usage. So in AWS, you will pay for something, right? Nothing is free. So you will pay either for network out or you will pay for scaling instances. And yeah, I will show you when it will approximately become problematic. I mean, when the trade-off is worth it. And the final test we did was when we had compression, when we had broadcast for both WebSockets and SSE, and here results are very similar. Maybe if I run more tests, the bandwidth will equalize as well, will be very similar, but for now, for some reason, not sure, maybe Socket.io adding additional metadata into messages, it's a overhead added here, but I think it will, if I will run more tests, maybe they will be more similar. Nevertheless, the conclusion from these results so far, I don't see the reason to use SSE because the project I'm working on, we have small messages and we send them frequently. So for me, WS is winner. Maybe if we will have like 50 kilobyte or a bigger, like 100 kilobyte messages, we will consider using SSE for broadcasting. But for now, just WS is a winner. And now I want to move to the next topic when we will discuss when to use compression and when not to. Just a brief pause. If you enjoy this type of content or want to watch me live code projects like this, hit subscribe button and ring that bell. It is free, takes 2 seconds, and helps me a ton. As you can see, only a very small percentage of you guys actually subscribe to my channel. Anyways, thank you very much for all the support. Let's continue. Here we have data transfer out cost for AWS. As you can see, for the first 10 terabytes a month, we are paying 9 cents a gigabyte, and then it decreases with higher traffic. So at a certain point, you would want to compress messages. And let's assume we will pick some instance like T3 large. And let's see approximately, I've prepared a diagram. So if we will, actually I used X large. So X large, if we will run it 24/7, it will cost us $119 a month. And let's assume that our compression reduces bandwidth by 70% and we will increase compression adds like 30% RAM CPU usage. Right. And yeah, I added a diagram and it will be in a Git repo as well. So approximately at 5 terabyte a month, we will be getting some benefits. So here I added cost reduction, but this is without free tier. So in the beginning, probably we will have free tier and the savings will not be as high, but nevertheless. So the instance cost in the beginning, we will have one instance and the cost is static. And then for the bandwidth, right, we, for example, of 5 terabyte a month, we're getting 30%, 70%, sorry, compression rate. So we are paying already, we are getting some savings if we don't have free tier. And then pretty much the same, right? At 2 terabyte, we are using 6 terabyte, we are transferring with compression. And then I think at around 5 terabytes, where really the benefits start to show up. right? When we have 5 terabytes, now we have 1.5 or a bit bigger. And here, let's assume more realistically, we will have more instances. We will need 7 instances, right? We will scale because we need to do compression. We're using more RAM. But nevertheless, you can see that now bandwidth savings are more important. And it will just continue growing, right? So let's assume then we will have 10 instances against 13 instances, but instance cost is becoming more and more insignificant. And then if we go like 20 terabytes, now it's $500 savings. Right. Even, yeah, we are now entering in the new zone of pricing and still. All right. So this is pretty much everything I wanted to show you in this video. I hope you enjoyed it. If you have any thoughts, let me know in the comments down below. And I hope you enjoyed it. Thank you very much for watching. See you next time. Bye-bye.